thanks for giving me this opportunity. And with that, I'll start my talk. Okay.
Yeah.
Good afternoon to all the participants. I hope all of you are familiar with at least some terminologies here. I'll once we start the presentation in due course, we'll have some discussion. So you can stop me in between if you want to have some clarifications, and because we don't have face-to-face contact now due to this COVID situations. Okay. So I'm going to talk on use of this particular meshless method called element-free Galerkin method in stochastic mechanics. So my application mainly discussion mainly concentrating on this particular topic, the stochastic mechanics. Okay, and why we want to use a meshless technique for this particular use. Okay, so before getting into the main discussion part, I would like to add something on about my institute. You may not be familiar with this particular institute. You might have heard about IITs and NITs. This particular institute, this Indian Institute of Space Science and Technology, it's a small institute situated at the southern part of India, Kerala. Actually, we are an autonomous institute. Okay, and we works under the Department of Space, not MHRD, and it's deemed to be university as well. Okay, and this institute actually started with an intention to provide human resources for India's space programs. Okay, and we have actually three BTech course. In that, actually, two are BTech course, aerospace engineering and avionics has been changed to electronics and communication. Now it's not there. We have electronics and communication. We renamed it, and we have a dual degree course on engineering physics. Okay. We also have a master's degree. So I belongs to aerospace engineering department, and in aerospace we have structures, thermal and propulsion, aerodynamics, and flight mechanics. I hope most of you are from civil background. I hope so. And actually, there are interdisciplinary courses where even civil graduates can apply. Say, for example, structures and design. I belongs to civil. Actually, I have all my degrees in civil, and I joined aerospace. And if you look at our structures division, many are having degrees in various, say, aero background is there, mechanical background is there. So it's a interdisciplinary kind of course. And if you look at the course structure, it will be almost same as what you study in civil structures. All the classes, DFEM, dynamics, all those things are there. Okay, so, and also there is one more course where civil people can apply is geoinformatics. There is a MTech course in Earth and Space Technology. They have three courses. And there are other courses, even mathematics, they have machine learning, and chemistry, they have material science. So many are interdisciplinaries, and they accept students from different disciplines. Okay, and we also have PhD students. We have very strong faculty. Almost 100 faculties are there. It's a small institute with only three BTech courses and few MTech courses. And 100 faculties only, and we take students in different areas of engineering, like structures, thermal propulsion, aerodynamics. These are some manufacturing, material science. These are some of our related areas in aerospace, and similarly we can find different areas in avionics and other science program. And we do take some postdoctoral programs, very few. Okay. So with that, actually, I'll go to my talk. But since it's a research talk, since I'm introducing some research topic, initially I will give some small introduction about the areas that my team is working. Okay, when I say my team, I as well as my students and my collaborators. Okay, so you can get me into any of this link. My details are there. Okay, and my publication details will be there, and my area expertise details will be there. So basically, I have my research interest. I work in computational mechanics, and I'll get into. So as I said, today's talk will be on elementary Galerkin method, And we have used this SEFGM, okay, a meshless method for different applications. So this is basically you don't have actually, if you look at FEM, you have elements like this. Now in this case, actually, you don't have elements, only nodes, okay, and that gives you a lot of flexibilities. Okay, so we'll talk about all those things, and we use it for Ringling analysis, as well as damage growth analysis, vibration analysis, nonlinear analysis, like some of our students works in this hyperelastic. And another interesting topic that we work is use of boundary node method, similar to boundary element, and we use it for acoustic problems. So along with Dr. Praveen Krishna, who is an expert in acoustics, so we combine Meshfree method and boundary node method, boundary element method to get boundary node method. So this is some sample problems actually for our students data. It's a muffler, expansion muffler problem. And also one main topic that today's discussion is we will discuss about the stochastic analysis. That is my major area of interest, stochastic analysis using EFGM. And in that, actually, we will discuss today about some of the topics that we are going to discuss today is damage mechanics, probabilistic buckling analysis of columns, and this is a new method proposed by one of my PhD students, improved response function based stochastic meshless method. Okay, and also I work on some of my students work on wavelet FEM and related areas. So basically, I'm looking for mesh reduction techniques, okay, where the practical difficulties that FEM cause can be reduced, okay, for stochastic applications. Okay, so and also when I group some of the areas, as Professor said, I work on sloshing. Actually, we proposed some two degree of freedom system to find the wave height as well as force. Okay, and then many of my areas are majorly concentrated on structural reliability and probabilistic analysis, like piezoelectric and bioinspired composite and structural reliability and fragility analysis of dams. Actually, it's with Dr. Robin Davis. It's very familiar to NIT Roorkela people. He was there, and now actually he's an NIT candidate. And also some studies on manufacturing studies and some simulation spine and some analysis using analysis of spine joints using FEM. Okay, so these are basically my area of interest, research interest. Okay, since all of you are some faculty members, probably you can motivate your students or viewers, or if you want to do PhD. We have regular PhD students and we don't take UAP. We only have regular PhD slots, and then there are some on-site slots exclusively for ISRO scientists, and we are now opening for other sponsored students as well. We are in the discussion of finalizing the rules and regulations for that. Okay. Okay, so with that, actually, we'll go to today's talk, use of elementary Galerkin method in stochastic mechanics. Okay, so as you have seen in many of my most of my research interest concentrate in either probabilistic method or stochastic method or reliability method. So if you look at the current engineering applications, okay, most of us do not want to get into this probabilistic analysis, right? It makes our life complicated. Okay, basically it makes our life complicated. Most of practicing engineering problems, actually, we don't get into that analysis. So but in reality, actually, if you even the small tension test we might have done in our lab, we have seen that we get different values for smallness. Okay, and in fact that gives you you take mean value sometimes, you take some design value sometimes, and most of the times we neglect the randomness. Okay, and in practical cases within plus or minus 5%, we don't worry much about all those things. But now, and basically we cater that with the help of factor safety and so on. Okay, but this factor safety is the one. See, for a practicing engineer, the moment you want to introduce this probabilistic concept, it makes your system complex, and obviously the computation time required will be more. Okay, So that is why actually till recent times actually we don't concentrate much on the stochastic analysis or probabilistic analysis, and we do only the deterministic analysis. And somehow we take care of the uncertainties associated with this complexities or material properties or geometric properties or loading or boundary condition with the help of the factor of safety. And in fact, the factor of safety has to be decided with the proper information of statistic, with a proper reliability study. So we have a structural reliability course actually in many of the institutes now. I don't know how many of you have gone through. So if you want to have some introductory concept on probability, probably the best book you can is there is a book by Ang and Tang. You can read that book. Okay. So basically, it makes our life complex, but provided now the recent advancement of computational tools and technology that helps us to reduce this computational time and can do the efficiently structural analysis or probabilistic analysis. Okay, this makes so this is still now it's still progressing. Okay, and it's finding its interest in our engineering applications as well. Okay, so basically when we look at the practical applications, the one method that comes to our mind is for numerical solution is FEM, finite element method. Okay, so where actually you discretize, or if you have a body, you discretize with the help of elements. Okay, and then see, you model your problem. Say you may have a physical problem. Okay, you model it. Okay, when I say model, in mathematically, physics of the problem has to be taken care of, or has to be modeled using a mathematical entity. So you mathematically model it. So basically, you will end up with a partial differential equation. So if you look at your elasticity, you might have studied, you will end up with equilibrium equations and with boundary conditions and different essential boundary or traction boundary condition. And since it's a boundary value problem and the governing differential equation is, since it is valid for the entire region, it should be, if I take a small region, it should be valid for that region as well. And so I can solve it for that region. So this is basically, that's a concept of FEM. And now, if you look at the current literature or current status of FEM, that is the most opted numerical tool for not only for structural application, many applications. Okay, and in fact, then the first option for stochastic analysis also use of FEM. Okay, and so it started in 1972 itself by Shinozuka, and still with so again they used the popular Monte Carlo simulation. So you just simulate. So you model, you make the model, structural model in FEM, then you simulate. So I say, for example, your Young's modulus is different, or if your yield strength is different, or say if your geometry thickness is different, you make the model. So every time, so you simulate once with one thickness, and every time you randomly generate the thickness or Young's modulus and simulate it. Okay, and it's going to be computationally very tedious process. Okay, just making a finite element model itself for a single structure, a deterministic model itself is a cumbersome, because if you have this stress concentration points or some geometric irregularities, then meshing itself is a very tough problem. Solver may be fast, but the pre-processing time for an FEM is it's a computationally tedious process. Okay, and again, so such say think about for the same structure for say 10⁻⁶ or 5,000 or 1,000 analysis, the time taken will be very high, and that makes people think about the so-called perturbation method. So this particular method is one of the most popular method now. Okay, because it is computationally highly efficient when compared to FEM. This makes use of Taylor series expansion. We will have a detailed discussion, and you truncate it with the first order or second order terms. Okay, and then you can get the statistics. So you mainly, in this case, you mainly concentrate only on first order or second order statistics, means mean or moment, mean or standard deviation. Okay, So in that aspect, even it can give better results, the accurate results up to 50% CV. Okay, so the only one disadvantage is your CV has to be less. If you want to use Taylor series expansion, the variability has to be within. So you are using a perturbation techniques. So means your variability has to be within some certain limits. Okay, and this is acceptable because most of our engineering materials and engineering loads have we do not accept more than say 15 to 20 percentage variability. Okay, so within that variability, this gives better results. Okay, so that's why this is popular, and most of the methods are developed based on perturbation method. Okay, so the issue with this is it cannot generate the probability density, means full probabilistic characteristic of the response cannot be evaluated using this particular technique. Okay, so even higher, when CV is higher also, this method fails, and you won't be able to get higher order moments. If you want to get higher order moments, you can get it, but the problem becomes more complex. And that aspect, Kaminsky, he proposed the generalized perturbation techniques. It's again based on Taylor series expansion, but he used a perturbation parameter, and he proposes that it can get up to better results up to 25% of CV. Okay, but still this PDF and CDF is not, you cannot get it. Okay, and for that you need to use Monte Carlo simulation, but direct Monte Carlo simulation is again tedious. So, and there comes the ad hoc response function method, so which is now, as per literature in 2009, actually till that actually it is known as the best method. Okay, it uses Taylor series expansion of system matrices. System matrix means stiffness matrix, and the response is decomposed into some deterministic part and stochastic part. With the stochastic part is discretized into different set of functions. Okay, found to be, we will have a discussion on that, but it has some demerits. It doesn't consider the cross dependency, and linear expansion of stiffness terms only they have taken. Okay, so then this method, this ARF method, has been applied to many different problems, say non-linear problems, eigenvalue problems, vibration problems. The same people, same group of people has been developing this method for different aspects of structural mechanics problems. Okay, and as I said, Stefano in his review paper stated that this is considered as the best method available in SFEM so far. Okay. So now, so far, actually, we looked at stochastic FEM. Okay, and FEM has, as I said, some issues. Okay, especially when you have mesh related issues. Okay, especially when you have problems with the stress concentration, crack growth. That is, even in the deterministic case, you have issues. So that's where actually people started thinking about mesh reduction techniques, like reduced mesh, less mesh. With the mesh, if you have less, then actually you can reduce the mesh. So there are methods like wavelet FEM, then isogeometric analysis, and another, the meshless method, and so on. Okay, now I will concentrate only on stochastic aspect. So stochastic aspect FEM gives me difficulty when you map. Actually, see, you have when I say stochastic, it can be two different things. Okay, you can deal with the random variables, you can deal with the random feeds. So when I take a problem like this, okay, a problem which is defined in X. So I take this part, I take some property here, saying smallness or density or E. E has a particular value here, and if I take diff, it can have a different value here. So that means the function of X as well. And when I take a different sample, I can have different set of function. Okay, so it becomes a function of X. Okay, we call that as random field. Okay, we call that as a random field, random variable as a function of space. It can also be a function of time. Say, for example, dynamic cases, it can be also a function of time. Okay, sometimes that we like we differentiate these with the random field and random process. Okay, the terminologies, but now actually they use both random field for or random process for both function of space or time. Okay, so it can be function of space or time. Then actually it has a correlation, and there exists a correlation between these two. So the correlation usually for practical cases it decreases, but there is a length scale associated with that, and that gives me an issue in my FEM, because FEM you have measures like this. Okay, and if I take a property in smallest here, it has a correlation between property here. So the correlation length, there is something called correlation length, which defines this decay. Okay, so if it is very small, okay, when this gives me the mesh has to be very small. So that issue I need to somehow sort it out, and that's where the use of meshless method comes in, or pigeon. Okay. So the possible alternatives of SFEM is, one is, as I said, wavelet FEM, okay, and where actually we use the properties of wavelet, the multi-resolution analysis. So if you have a regular domain, actually, you need to have, say, one element only, and you can have its resolution, multi-resolution properties, depending upon which wavelet you use. You can increase the number of nodes, okay, without affecting the mesh. Okay, and you can get the higher resolution results. Okay, so even with the regular geometry, you may have to use more than one. You cannot use single element, but still an element is required there, but less number of elements compared to FEM. Okay, and similarly, isogeometric analysis is a new area which developed by, say, in 2000. In after 2010 only it started developing. Okay, so stochastic isogeometric analysis is a very recent hot area. Okay, and but in all these cases you require a mesh. Okay, a minimum amount of mesh. Okay, so another alternative method is stochastic meshless method. Our discussion today's talk, basically we concentrate on this particular aspect, stochastic meshless method. Okay, and when I say meshless method, it doesn't have mesh. Okay, it doesn't have elements. The concept of elements is not there. Okay, so we can solve the meshing issue. So I don't know how many of you are familiar with the meshing in any of the softwares or any of the complex problems. So it takes a lot of time actually. If you want to model, say for example, I was talking about spine. So if you want to model a spine and mesh it, it takes huge amount of time, okay, because you have a lot of small moving parts. So if we want to use actually a mesh, actually you have to just throw the nodes. You don't need to worry about so wherever you require, but still you have to concentrate your nodes. Okay, you don't need to worry about the aspect ratio and such things. Okay, so we can just put the nodes there, okay, randomly. So you can model discontinuities, cracks, and so on. Now we will have this comparison. This particular table we will look at it once again, or we will have the difference between FEM and Meshfree after completion of this after first few slides. Okay. So if you want to have more understanding on Meshfree method, I recommend you to read this particular book by G.R. Leo. There are different Meshfree techniques, okay, and for our discussion, we will concentrate on EFGM. Okay. So basically, the main difference I'll just point out and go. So you have elements in FEM and then shape functions. Okay, all of you know that if I take a linear element, okay, I'll in FEM actually, I'll write in this manner. So I'll write n1 u1 plus n2 u2 in FEM. Okay, where n1 has a variation of 1 to 0 and n2 has variation 1 to 0, and then you superimpose, or you have interpolation n1 u1, Lagrange interpolation will be used, or in some other case you will use say for example beam. There you don't use Lagrangian, they will go for other interpolation techniques. Okay, and then you develop element equations, okay, then system of equations for elements. So you will get, for each element you develop k u equal to f, and then you assemble it. Whereas in Meshfree actually you have only nodes, okay, and you don't have an explicit expression for shape function, okay. So when and where actually, or then and there it is required at that point. Suppose if I want to get the shape function to be evaluated at that point, say for example integration point, I will evaluate the shape function at that particular point, okay. So you don't have explicit shape functions associated with these nodes, okay. So, and you have, instead of each node has a domain of influence, and you will look at the points. So the nodes which are influencing that particular point, and it will the contribution from that nodes will come into that particular point, and that will be added to your global stiffness matrix, okay. So the equations for nodes, and then you will see which are the nodes influencing, or which are the points that was influenced by that particular node, and then accordingly you populate your matrix, and then apply the boundary condition and solution. Okay, the same procedure in FEM. Okay, so with that, okay, so I'll skip these slides. Okay. Now to get into Meshfree techniques or EFGM, let's start with this. This is something which is very familiar to all of you, least square approximation. So I have, say, n points at different positions, and scalar values I have. Okay, I want to fit a curve. That's what, how do you fit a best fit curve? So then you use a least square. You use a polynomial basis, and you use unknown coefficient a, and then p transpose a. Okay, you approximate a function depending upon the continuity requirement. You can have a linear, quadratic on x. When I say polynomial basis, on x, x square, x cube, and so on. Okay, so whether it's a linear basis or quadratic or cubic, or you can have, if it's a two-dimensional case, then you have one x, x, y, x square. So you'll have a Pascal's that triangle. Okay, you can take the variables from there. Even you can have sinusoidal functions. Okay, so vector of unknowns. Then you use a least square. Okay, the function, approximate function minus scalar value, you square it, then you do a minimization to get AI, evaluate AI. So a will be a function of all the xi's. Okay, each a. The problem with this is each of this a is, suppose I have n points, I have say 10 points. Okay, so this a is a function of all these 10 points. Okay, if I change the 10th value, okay, so if I change the 100th value or 10th value, then the value of a that I get will change. Okay, so that is the issue with this. It is non-compact. Okay, and so people started thinking, because in many practical cases it need not be. Okay, and then people start thinking about weighted least square. So you just weight the approximation with a weight function. Okay, something like this. The least square function will be weighted, so it has non-zero values. You have some fixed points. Each fixed point has a weight associated with that, and then this will be, the function will be weighted with this. Okay, so this makes your approximation compact. Okay, it has a compact support, it has value on the compact support and zero value on the other support. That's how the weight function is defined. Okay, and then solve for a. So a will become function of this xj's. Okay, this particular xj has a particular a values, okay, set of a values, and others will have other values, and you have to connect somehow. Okay, and then actually people start out, so you have to connect it then. So why don't you, instead of fixing a xj's like this x bars like this, why don't you move it? Okay, each point you can do the minimization. Okay, and there, that is a point. Actually, the concept of moving least square has been proposed by Lancaster and Seligers. So the idea here is start with the weighted least square. Okay, then move the point of the entire parameter domain. Okay, you fix the point, and you fix the point at that point your associated weight is been applied, then you move the point. So how do you move?
So you move the point, and every point actually you can do the minimization. So if you take a particular point, you look at which are the nodes, which affect that particular. So x2, x3, x4. So that will come into my approximation. So another way of moving is you fix the weight for instead of the fixed point, you fix the weight for all the associated nodes, and then move the point alone. Okay, and again you can look at say again, if I look at this particular point, again 2, 3, and 4 has been affecting this particular point. Okay, so at x bar equal to x, now at this point you do a minimization. Now if I take another point somewhere here, I'll have to do a different again minimization. Okay, so basically what happens is at each point you have your a values will be different. That means a is going to be a function of x. Okay, so that's why your approximation has to be something like that, p transpose ax. Okay, so every point a will change. That is the meaning of a as a function. This meaning is different. Okay, this x is a continuous function. At this particular point, a is it's a scalar. It's not a function of x. Okay, but overall it changes. If I take a next point, it has a different value. Next point has a different value. So it varies with respect to x. Okay, that is the meaning of this. Okay, so moving least square approximation is what this, and this is the basis of EFGM. So we use this for the meshless method. Okay, EFGM. Okay, so in EFGM our approximations will be something like this. Okay, let's okay, so this is the characteristics of this moving least square. So a of x itself has a function of x, and one major thing is the continuity and differentiability depends upon the continuity and differentiability of the weight function. Okay, so this is a important characteristic. Okay, and in the limit each of the point in space taken for optimization, we get the best possible weighted least square fit. So you'll get a very smooth curve, and it will be the best possible weighted least square fit, since you are doing the minimization at every point. Okay, and we don't need to worry about xj. You don't need to worry about xj, and then you have to connect it and so on. Okay, now the problem here is choice of the weight function. Okay, which weight function, which will give the best value. And how do you find this influence, domain of influence? Okay, you take a point, so you have to define this domain of influence. So that is another issue. We will have a discussion on that in the coming slides. Okay, so there are a number of Meshfree techniques developed, and today's discussion we will concentrate only on elementary Galerkin method developed by Belisco et al. In 1994. So you can just search for Belisco's paper. Okay, a paper by Belisco and Tolbo that gives you, say, if you want to start working on it, Belisco's papers are very good papers, very neatly explain the basics of elementary Galerkin method, and in fact some MATLAB codes are also available in one of his paper. Okay, so introductory papers are very good to start with this particular technique. Okay, so in EFGM, it's very similar to FEM, so that's why it became popular. Okay, and we use again moving least square approximation, and we will use the Galerkin weak form for discretized system of equation as in FEM. So that is why it has a similar formulation as in FEM. Okay, so this is the paper I was talking about. This paper, if you look at, you will get MATLAB code for implementing 1D and 2D elastic problems. Okay. And the main issue with this is essential boundary conditions. So we will discuss about these papers in the coming slides. Okay, so basically this is a formulation. The shape function construction will be something like this. So you have a displacement approximation. As I said, we will use moving least square. So it will be P transpose A, where P A will be a function of X, which is not in FEM or any other approximation. Okay, so then the least square weighted part, least square L2 norm will be written like this. Okay, you square it, and where di okay, is actually in FEM it will be nodal values or displacement values. We call this as a nodal parameter. We'll see why it is called a nodal parameter, not the nodal values or not the displacement values. We'll see in the coming slide. Okay, so we call this as a nodal parameter. So for the time being, you believe me. Okay, you have to be with me. Okay, so like this defined. Now the weight function is defined in such a way that it has a particular domain of, so every nodes or every point has some domain of influence, and suppose this blue point, you can see this blue point, that is my point of interest. Then you have to see which are the nodes that is influencing, whose domain of influence are covering this particular point. So all the red points are covering this. Okay, so that means there are three nodes which influence this node. So that nodes will come into picture when we take that particular j of x. So I is equal to the rest of values, actually w will be 0. Okay, the rest of the nodes w will be 0 at this point. Okay, so that's how we select the domain of influence. Okay, so once you do that, actually you have to do a minimization. Okay, so in minimization, then you will get, you can write everything in matrix form. Okay, you can write everything in matrix form, and if you sit and write down this, you will get in a nice form. Okay, as A inverse C of x into D, and you just substitute back into my original P transpose AX A, you will get the shape function. So finally your approximation will be, you can write it as phi transpose x to D, where phi is nothing but P transpose A inverse C. Okay, so this A and C are again functions of this basis function as well as weight function. So when you select A is of form like this, 1x1 square if it's a linear basis. Okay, so when we take the domain of influence, we need to make sure that it has sufficient number of nodes that A inverse exists. Okay, so usually if m equal to 2, okay, at least two nodes has to be there. Okay, and so that's how the shape function. So it doesn't have an explicit expression. So it's a function of A, C, your weight function, and that particular point. So at if you want to evaluate phi at a particular point, say xj or xi, you just pass xi there and get the, you look at which are the nodes influencing, then construct this and evaluate this. That's how we do this. Okay, now let's look at the effect of weight function. So as I said, the weight function has an important contribution in this. So if you take a weight function like this, these are the actual nodes. I don't know if it's visible or not. These are the nodes. Okay. Now if you take a weight function something like this, the approximation that you get is something like this. It's very linear. And if it's take a germ function, hat function kind of things, then you get like this, like a piecewise linear approximation. But if you take a weight function something like this, a Gaussian kind of thing, okay, or a cubic spline kind of thing, a smooth function like this, and you can see a very smooth function like this, you are getting, okay, a best fit line, and the curve is so smooth, so the continuity and differentiability of this particular function is dominated instead of in FEM actually the basis function determines that, but here actually the weight function determines that. So the advantage is you don't need to worry about stress gems or stress irregularities at the element boundaries as in FEM. It's nothing sort of that is there in this particular case. You have a very smooth derivatives as well, you'll get. Okay. Now the weight function options, actually there are plenty of them, and one of them is see, different people have referred use different distributions. So as I said initially, the selection of weight function is a issue here. Which one? So some people have used T distribution function. If you look at Giarlio, he has specified cubic splines, cortex splines, exponential weight function, and in fact for our engineering problems, as solid mechanics problem, cubic spline or cortex spline is sufficient. Okay, if you use exponential T distribution, you have infinite derivative, and we don't need to have actually, but this can be a suitable one. So cubic spline or cortex spline can be suitable. Okay. So here, as I said, again, the weight function is defined in such a way that it has value within a particular region, and beyond that, it is 0. It need not be we can have a rectangular wave function system. Okay. So the properties, if you look at it has partitionality, okay, and linear projection. All these properties, as in Lagrangian shape function, it also MLS shape function also possesses all these things. However, a major property that Lagrangian process doesn't have, MLS doesn't have. Okay, so the chronicle data property, and that creates a lot of issues actually. Okay, that means if you have if you pass xi, I will not get so if I evaluate at I should get 1. Okay, but it is not. So for example, in FEM, if I have an element like this, if I have an element like this, okay, and if I my n1 and 2, if I define, so n1 at, say this is at x1 and this is x2, n1 at x1 is 1 and n1 at x2 is 0, right? Similarly, n2 at x2 is 1 and n2 at x1 is 0. Okay, so this ni at xi, so I can write this as ni xj is delta ij. This is called chronicle data. Okay, when I equal to j is 1, but that property is lacking in this case. Now this creates an issue because the approximation need not pass through the nodal displacement values. Okay, it gives me a best fit curve, but as in FEM, actually your approximation pass through the nodal displacement curve, right? At nodes, it will exact. It doesn't happen in. So if you pass your, say, n1 u1 plus n2 u2 is my approximation FEM. If you pass x1, so u equal to this. If you pass x1 here, then I will get u is equal to u1 because n1 equal to 1 and n2 equal to 2. But that doesn't happen here in meshless. And especially the problem will start when we deal with the boundary conditions. When you deal with essential boundaries as well as if you have material boundaries, okay, there actually you need to exactly satisfy the essential boundary condition, otherwise you will get into problems. So people started thinking about how to deal with that, and then they proposed different techniques. So we will see that in this. Okay, so generally, so if you have a 2D problem, this is how the governing equation and the boundary conditions are specified. As in FEM, we are dealing with peak form, either variational form, or we can derive this using Galerkin weight residual method. Okay, so the simple thing is variational form. Okay, so you derive the variational form for this governing equation. Okay, then you apply the boundary, the approximation here. Okay, so and it will decrease into kd equal to f. Okay, now you have integral equations here. So if you want to integrate, you have to use a numerical integration, and the numerical integration that has been used for FEM will be used here. And in that case, you need to have a cell, because if you look at Gauss quadrature, it is defined from -1 to +1. Okay, so that means it is defined within a cell. So for that purpose alone, in EFGM, for this particular elementary Galerkin method, you define a background cell. Okay, it doesn't have to coincide with the displacement nodes used for displacement approximation. Okay, the nodes that is used here is different from the background cell. You don't need to, when you update your mesh, you don't need to change your background cell. Okay, and due to this presence of background cells, even the people who object to EFGM, they call this as not an element free, or it's not a pure meshless, it's a pseudo meshless method. So okay, whatever may be, this in EFGM, this particular mesh has to be there. So this cell has to be defined for numerical integration. And once it is done, then you will get a discretized system kd equal to f. Okay, but then how do you apply the boundary condition? okay, whether you can get it or not, if the essential boundary conditions are not satisfied. So whether we can get it in this form, that is a question. Okay, so issue is this. So this is your essential boundary. This particular point is your essential boundary. So now at the essential boundary, this is the nodal value that I am expecting, but my approximation, this is the nodal value that I am getting. By my approximation goes through this point. Okay, so how do I get it? So you have to use some additional condition. So either you have to apply, so I'm applying additional force, and then you have to push that point alone to, did you look at that point alone to this? So you have an additional constraint equation there. So you have to push it to the nodal value. So I have to make sure that nodal value and nodal parameter are same at the boundary. Okay, this is what the Lagrange multiplier do. You have an additional force, okay, which push the method. So those who have studied optimization, or those who have studied even SEFGM, we use this. Okay, so Lagrange multiplier technique, or even you can couple this point alone. You use a SFEM. Say at this point, essential boundary, you use a finite element mesh, and rest of the portions you can use meshless method, or you can use a penalty function. You use a penalty factor and try to force it. Then actually you, and there is another method for transformation method. Okay, so all this method has issues. We will just have a quick look at Lagrangian. So when you use a Lagrangian like this force, due to this force there will be a work done. So variation form will have a additional term, okay, where this force times this difference in displacement has to be there. Okay, and that create issues like you will have equations, you have diagonal zeros, and so you have to use some special techniques to solve this. So he come up with transformation method. This is the transformation. So he wrote this D, the relation between D and D cap, as D inverse, gamma inverse D, and this gamma is a fully populated matrix. Okay, and then you just multiply this. This is orthogonal matrix. So you can split the equation, you can uncouple the equation into two, and then you solve it, apply the boundary condition, because you are written in terms of D. So this makes these people, Sanida et al., to think about directly apply this. Instead of doing all these things, why can't we apply directly into this and apply as in FEM? So they have made this suggestion. Okay, but then again, actually you have inverse of a fully populated matrix, because IC is very large. You have only some 5 nodes in your essential boundary condition and 1000 nodes in your domain. Your matrix has to be 1000 by 1000, or if it's a 2 degree of freedom system, 2000 by 2000, and so on. Okay, so that point we come up with a different proposal to scale the this approximation at the boundary alone. The approximation itself, we use a scaling matrix, a gamma inverse, so that it go through the nodal values and nodal parameters are same at the boundary. So you get an equation like this, where you can directly apply essential boundary as in FEM, and we can get more details in this particular paper. Okay, so it's not a fully populated matrix, so the number of operations will be less when you take gamma inverse. And this is just to show both the methods give same results. Okay, it's a curve fitting example. So I used MLS to fit the curve. I put a constraint that curve must pass through 1, 7, and 10. So you can look at this point. The black line is the MLS approximation without any constraint, so it doesn't pass through that. Now, if you apply the method suggested by Sunita or our method, both will pass through. With an advantage, it has only nodes associated with the 1, 7, and 10. The rows associated with 1, 7, and 10 only is populated. Okay, others are elements of an identity matrix. Okay. So basically, this is the algorithm. You set up the background nodes and integration cells. You set up the nodes, then set up the weight function and its parameters, material properties, fifth the integration rule. Okay, you can use 1 point, 2 point, 4 point, 8 point, and so on. loop over the integration. You start your loop at the integration points, and for each integration points, determine the node, neighbor, calculate the shape functions, and then calculate the B matrix, K matrix, and so on. Okay, and then assemble the force matrix. Okay, enforce the boundary and enforce the boundary condition. So assemble the force matrix, and you complete the loop here. Okay, then enforce the boundary condition. Okay, solve for nodal parameters. Okay, that is the EFGM algorithm. Now, if you compare the Meshfree method and FEM, as I said, the shape functions are constructed using elements in FEM, but here using at a particular point of interest during the analysis and not before the analysis. Okay, moving this curve technique is used in meshless, whereas other techniques are used in FEM. Okay, so element connecting nodes are not required in Meshfree method, but in FEM we have local element stiffness matrices. They are first constructed and then they are assembled together to get the global matrix, and then apply the boundary condition and solve it. Okay. Continuity approximation depends upon the continuity of the weight function, and so it can produce continuous derivative output. Okay, in meshless. In contrast to FEM, where you have element to element connectivity is not there for derivatives. So your displacement is continuous, but if derivatives are not continuous, you will have strain jump between the elements. Okay, in FEM. Okay, you have to do some other technique to come out of that. Okay, so now with that I come to stochastic elementary Galerkin method. Oops, time is 4, so I'll have a quick. Okay, so this has been integrated. So this has been initially this work has been started, I think, in 2000 or that region, that era. Okay, so initially the FEM was used. Then actually people started thinking about the EFGM. Okay, and the first person who worked in this is Professor Rahman's team. Actually, Professor Rao was my guide, and Professor Rahman in Iowa State University. He and his group started working on stochastic meshless method. So they used perturbation method initially. Okay, and they used it for elastrostatic analysis. Okay, they used MCM multicolor simulation to validate. Okay, and then first order and second order perturbation, and they found a very good results. Okay, matching with the perturbation. So first order, actually you can see as you increase the coefficient of variation, or okay, the variation between first order and MCS is increasing, but up to 20%, at 20% you get a better match. And this is MCS, actually the standard deviation, but it deviates. So probably up to 15% we can use perturbation. Okay, and they extended this work for finding out the reliability. Okay, or probability of failure, and so on. Okay, later, and there are several works from that team, same team. Fracture mechanics, probabilistic fracture mechanics, stochastic meshline, elastoplastic crack structures, and so on. And this is one of our paper, so we applied it for elastoplastic damage analysis. We will have a look at in this discussion. And then their team, actually, again, there are other people who worked in spectral different other techniques other than perturbation. Okay, and also it's applied for bending analysis of plates. Then there is another technique called polynomial Kavos expansion. Okay, along with it's a spectral decomposition. Okay, they used it for that. Then there are set of works which is going on this particular area. Okay, now we will concentrate our main work on this particular work that we have done. Okay, stochastic damage mechanics. So first you need to see whether actually is it stochastic in nature or not. So the main thing is, if you look at if you try to take a bar and try to bend it, okay, you can see that some bar may take 1000 cycles, some bar 500, some bar. So that means there is something which exists that makes it the number of cycles is random. Okay, so it can be micro cracks or micro voids. So that means there exists a micro voids which is random in nature. Okay, so there is an uncertainty associated with presence of initial damage. So this particular work damage is something which is considered as random, and we assume that there exists an initial damage which is random in nature. Okay. So as a tool, we took Meshfree method, and the objective is to develop a Meshfree method, stochastic Meshfree method for damage analysis, and it should be elastoplastic damage. So material nonlinearity is the main contribution of this work. Okay, stochastic. So that so far nobody has been worked on Meshfree method for nonlinear analysis, and to have a just continuous damage growth analysis. Damage is a very simple parameter which is defined as the area of voids to total area of that surface if you take a representative volume element. Okay. So there are different damage parameter. This is called damage parameter. This is what Kachanov has defined. Then actually effective stress concept, because when you have change in area, your stress will be changed. So sigma by 1 minus d, there is an effective stress concept. Then equivalent strain principle. So Young's modulus can be treated as there will be change in Young's modulus. Okay, the moment you have damage. So such theories are used, and we will be using in this particular work we will be using a isotropic unified damage law, which is suggested by Lemaitre for ductile material. Okay, so this is basically 1 minus criteria which have this plastic along with the potential. We have a damage potential which we observed experimentally with some parameters, and the corresponding evolution laws are also defined here. Okay, so if you take some plasticity books, plasticity course, you'll be familiar with these type of variables. So I will not get into that. So you have a governing equation, okay, as in as usual. Then you have a variational form. You apply the approximation, you get the matrix equations. This system of equation is a matrix form. Okay, and since it's a nonlinear equation, you have to use nonlinear techniques to use solve this, and we use Newton-Raphson. Okay, this is a deterministic analysis. Okay, so you finally you get k delta. You have to do incrementally. Load increments you have to give, and you have to solve it. This is about this is the flowchart explaining that. So the issue with this is if you have a material nonlinearity problem, so you have here actually you have a nonlinear Newton-Raphson has to be used, and finally you have this potential function which has to be solved. Again, you have to use a stress update algorithm has to be defined. So in this actually, since we need to implement a stochastic implementation also is pending, so we used one of the simplest method to solve this, which is proposed by Professor Shivkumar and Noyadis. Okay, we convert this into a quadratic equation. Instead of differential form, we use incremental form of delta. So actually, this is sigma e dot. Okay, and we write this as delta sigma e. Okay, and then you get a quadratic equation. This particular failure function is giving you a quadratic equation. You can solve for delta lambda. Okay, and then solve for the incremental stresses and strains and so on. Okay. So this an example problem we solved using plate with a hole with an initial damage. Okay, the damage will starts to grow when plastic strain is accumulated. So that critical value is taken 0. So the moment its plasticity starts, the damage will also starts to grow. Okay, the number of nodes has been fixed by a proper convergence study. Okay, and this is the final result. So you can see that there is a damage flow in this direction. Okay, and this particular you can get more details from here. And so now when it comes to stochastics, so this is what I was telling. So when I take actually a particular cross section, I have d1, d2, d3 different values, and I can represent these using a histogram and the density function. And if I take a different section, again you have different histogram. So finally this is going to be a function of x, and it is random also in nature. So basically you are modeling inhomogeneity using this. Okay, so we call this as a random field. Okay, and you don't have an explicit expression, so that makes your life complex. of x is a random field, and for this particular work we assign a log normal field, okay, with some mean and standard deviation, and this is the correlation function. Okay, usually many of the papers they use this correlation function as exponential function, but it has a issue with x is equal to 0, especially when you use series expansion techniques. Then this gives me difficulty in convergence, okay, this particular issue. So then actually you may have to use a modified covariance function proposed by Spanos. Okay, so you can see this is the exponential. You can see at x is equal to 0, it is the derivatives are doesn't exist. Okay, how this is a very smooth transition. Okay, so I have this log normal field, and what I do is I'll convert that into a Gaussian field by taking exponential function. And the moment I have exponential field, it's symmetric, Gaussian field symmetric, and when I use some Taylor series expansion and take the expectation operator, the even times only goes. I can reduce the number of terms. Okay. So the equation, the moment you have those material properties are random, your equilibrium equation is random in nature. Okay, and that makes your life complex, and you need to have a model. So as I said, you don't have explicit expression for this, so you have to somehow model it. So a simple method is, there are different techniques. If you look at, we call this as random field discretization. There are a number of techniques. You assign some random variables. So what we do is we discretize into random variables, and we use a shape function like in the displacement approximation, and then you get an expression for that. So that is one technique. So then you substitute here. Now another technique is something known as scale expansion. Okay, this is a spectral decomposition of autocovariance function. This your random this autocovariance function is kind of inner product. So you can get the spectral properties, and you can expand using your eigenvalues and eigenfunction. Okay, so you finally this is how it looks like. You have to get the eigenvalues and eigenfunctions, and you random field can be modeled using this. Okay, so either of this or any of this is one of the most efficient technique, but it will always underestimate your final results. Okay, so because your eigenvalues, you can see that eigenvalues will decay like this. So you can constrain. So first few eigenvalues only comes into picture. This, okay. So finally, your equilibrium equation will be function of discretized set of random variables. Use Taylor series expansion. Okay, you want to get the mean and standard deviation, you use Taylor series expansion. Okay, at mean equal to 0, this is a zero mean process. So you can apply that. Okay, and then you get some expressions like this. Okay, if you pass expectation operator of this. So you need to find the derivatives of this ui and first and second derivatives. Okay. Now that is the main issue. So for that, actually this is my equilibrium equation. Okay, use Taylor series expansion on both sides, simple techniques. Okay, and then pick up the terms of equal order. So you get three sets of equations. Since I am interested only of the second derivative, I will take only up to second order terms. Okay, and since you have a nonlinear function, okay, all these three equations are nonlinear in nature. So all the three equations has to be solved using Newton-Raphson to get the. So if you solve first, actually it is like a deterministic solution. You will get k delta d equal to f. You get delta d, and from the second equation you get derivative of the displacement, and third equation you get the second derivative of the displacement. And once I get the displacement, then I can use my approximation to get delta u, delta ui, and delta uij, and substitute and get the statistics of displacement. To get the state variables, you have to solve for this plastic multiplier. Okay, so again you will have an issue here. So what we proposed is, we propose to use again Taylor series expansion with this. Okay, a stochastic stress state algorithm has to be proposed. So again use Taylor series expansion and find out the derivatives. of lambda as well. Okay, so this is the final flow chart. You have a, and skip all these things. So see some of the examples solved. Okay, you can see that this different techniques has been used, and all the techniques are matching well. But see, you can see the smooth curve that is obtained by MCS, whereas the perturbation techniques actually it fails to capture the smoothness. Okay, so at the load, when the material property changes from elastic to plastic, you can see that there is a jump in it's failure. You can visible that in some other see here. Uh, yeah, here you can see that this is a plate with the hole problem. Uh, Plate with the hole problem, or it's a 2D problem. You can see that the sigma 2 to is smooth. However, this is effective stress. However, at this point it fails to capture. Okay, the smooth variation. You have a sharp. Actually, in this case, I have considered linear elastic linear hardening. That's why that happens. Okay, and so this method actually is useful for a predicting the stochastic damage analysis, and this details can be obtained from this particular paper. Okay, and we extended this to elastic buckling analysis problems. One of our BTech student worked in this, and you can get the details. So what we found out is the statistics of eigenvalues, means the buckling load, first few buckling loads in standard deviation using different techniques, and also the mode shapes. So this is a simply supported first mode, second mode, and different columns with a different boundary condition. And very recently, actually, we come up with a improved response function based stochastic meshless analysis. Okay, as I said, the ARF method was proposed by Folsom, which is known to be a best method so far. And we thought of implementing, that was proposed originally for FEM. We thought of implementing it for a meshless technique, and we implemented it. And then we found that it can be improved actually. Okay, the ARF method actually, these are something which we discussed. ARF method which works something like this. So use Taylor series expansion for stiffness metrics, whereas the displacement is discretized into set of functions. So each displacement function is set of individual beta. So this is d1 of beta 1 plus d1 d2 of beta 2, and if you pick the terms, actually you'll get a discretized through set of equations, and then you solve for each of this d1 separately. So this is how ARF method has been implemented, and it's an effective method, and you can use Monte Carlo simulation. So you don't need to every time you don't need to use, you get explicit expression for this in terms of beta. So you don't need to every time, you don't need to set up this equation and solve it. You can directly simulate this particular function alone. Okay, so you don't need to do a FEM simulation every time. That is the beauty of this. Okay, so you can save a lot of time. And what we proposed is we just improved, we just changed the ARF method. With a different approximation. So this actually we have written as a function of all the variables. So the cross dependency between beta is also accounted here. Okay, and rest of the things are same. We just modified this with this. Okay, and that gives the like the results that we got is actually very interesting. Okay, so finally you have an expression for beta like this. So you can just simulate it using MCS. Since K0 and Kij are independent of this beta, you can evaluate only once, need to evaluate only once outside the simulation. Okay, so you don't need to evaluate every time as in MCS. Okay, that saves a lot of time. Okay, when you just simulate beta, substitute in this expression, get the delta D. That's what we do in IRF method. Okay, and we have solved several methods, and we can see that even up to 30% of CV, this ARF, IRF, and MCS are matching well. Okay, so it gives a better results even for higher CV. Okay, and that is what we observed. Even Even I can get the PDF and CDF using this because we are using MCS and matches well with the MCS. And one of the interesting observation is the time. Okay, the computation time is also very less compared to MCS, and it's comparable with the perturbation technique. That is the beauty. Okay, it's comparable to perturbation and gives me all the probabilistic characteristics. So we extended this work for different problems. In fact, beams, okay, and so in all the cases we could get matching results, and we were able to get accurate results or the best results so far. Many of the stochastic this techniques has been given. We used it for even for a frame, okay, a practical problem, two story frame, one-way frame has been solved, taking smallest as the bandite. Okay, the displacement, I think both mean and standard deviation at some points, the horizontal deflection, vertical deflection, even rotation. And we found that this IRF and MCS, you see the match. This is how we got exactly same similar results we got up to, if you look at the second decimal, it is matches well. And so fourth or fifth only we found some difference. Okay, so this is how the PDF and CDF also, and computation time is also very less. So this can be treated as one of the best method. Okay, and this particular work is now in press in computer methods in applied mechanics. So this method is very useful for solving when the properties are symmetric. Okay, the random field characteristics are symmetric, and even for log normal can be used. We have used it for log normal, but other probabilistic distributions, actually it's still an open problem. We are working on that. Okay, so I'll conclude my talk here. So with this, actually what I want to tell is EFGM, a meshless method, is an efficient, maybe other meshless method also I didn't try with that. So EFGM is found to be, to my experience, found to be an efficient numerical tool for problems in stochastic mechanics. So with that, I will stop my talk today. Okay. I know that it is a very tough to yeah. So, but if you take something, some ideas from this, and if you go back and if you search it, that will be sufficient. That is what my objective is also. Okay, if you want to do some research in future, you can just search for some of this topic in Google and get more details. Okay.
Thank you. Thank you, Professor.
Yeah.
Actually, what happened? Those participants don't have any experimental facility, and only they have laptop. They really can start. They are doing research in this topic. Though it is fully mathematics, but you have to accept that this type of people are taking that pain to understand all the concept, not only understanding and also implementing the concept in the real life problem. Okay, so this Professor Arun and this community who are working on the coding, they are really taking that pain, not only for understanding, not only for giving a lecture, but also solving some real life problem. The problem you see, sir, have solved some plate with a cutout and frame problem. Okay, so the simple problem that also can be solved in your laptop, but you have to again take that pain. You have to understand all the finite element method. Then you have to learn what are the in the finite element we are doing the meshing. Then you have to basically learn that weighted residual technique, because the finite element basically based on the Galerkin. Initially, probably it was started with the Galerkin technique, and later on, basically that your Meshfree technique come to the picture. Okay, so Sir, I was asking, can you share some short code or small code to the participants so that they can start their journey? Now, those code which is not useful to you, but that can be useful to the beginner. If
That's
you
what
have,
if you look at the paper by Belisco and Dolbo, okay, they have a working code actually, working code for.
okay,
We can see. No, I'll make a spelling mistake. Belisco. If you look at Belisco's site, he is no more now, and Dolbo.
yeah,
Okay,
Belisco probably died on a few years, 2 years back, probably 2 3 years back.
So John Dolbo, he is the editor of that finite elements analysis and design. So they have given paper introduction to meshless elementary Galerkin method programming. Okay, probably I can send that paper.
Yeah, that will be beneficial for the participant.
It is having the code, MATLAB code for 1D as well as for 2D problem. Okay. Working. And I think that is available in their site as well. Okay. In Dolbo's or Belisco's site, it is available. So actually, I started working on. I started my work with that code only.
Yeah, because somehow they need to have something to start their journey. Otherwise,
that paper that you can download that paper actually. That will be a good initial. To initiate the work on meshless method, that will be a paper. Okay. So I suggest those who want to work, I suggest to read that paper and take that code and read line by line along with the paper. They have an algorithm. Otherwise, you won't understand. First, you understand the technique, then you go through the code.
First, they should have that concept of finite alignment, that regular finite element. Otherwise, it will, because that essential boundary conditions, Dirichlet boundary conditions, they should know that why it is essential and why.
The background of finite element method is necessary.
Yes. After that, actually, you can start this, because once you understand that concept of finite element and are able to do coding of cell element, if you're able to do the cell element, I think thereafter all the things will be clear to you, because in the cell element you can have that concept of shape functions, and then how to do that your element, all the things, how you are interpolating, extrapolating that displacement, all the things are there. So once you are able to do the coding of cell element in a finite element, thereafter you can start the journey of if I am correct, probably I am saying that right thing, otherwise Professor Arun can correct me. Then after that, you can start that Meshfree, and sir is saying that there is freely available code. You can copy the code or you can type the code in a MATLAB and you can start your journey. But again, you should start solving small problem. Don't think of solving a very complicated problem, because you will be lost in that, either in the problem itself or in the coding, because you are not knowing which result is coming, whether you are doing mistake in the coding or the problem or the problem you are solving. Okay, so both the way, and also you should verify the result, because each step in the coding you need to verify. Otherwise, again, you will be lost. You at the end of all the things will find there is no error, because in that coding it used to happen. You are doing all the things and you are saying that no error is coming, but result is not matching. That is the horrible things of doing coding. If you are getting error, you will be satisfied. Okay, I am doing some mistake.
Yeah, if any of them, if they want to work and if they have some doubts, actually, you can feel free to contact
me.
Yes. And you should motivate your students to do MTech or even for okay.
Sir, in this slide number 25, you have mentioned various Meshfree method, SPH and various method.
Yes. There are several techniques.
Yeah, so actually, is there anything that this method is suitable for one type of problem and other method is suitable for other type of problem? Is there anything, or all are equivalently good?
No, I don't have much idea. See, usually SPH they use for particle method.
Yeah, particle method.
Yeah. And MLPG and EFGM has been used, even RKPM, all this has been used for solid mechanics problems.
Okay.
Okay. And why I took elementary Galerkin method is, okay, one is like my grade was working in that, and then I found that, see, all this method, they say MLPG also says that it's free of meshes, but finally at a local point. So the
Okay.
technique is actually in all these cases, some techniques are different. Either weight function or the way the integration has been done. So, but still all this has to do some integration to evaluate the variation form. Okay, in elementary Galerkin method, actually it has similarities with FEM. Those who knows FEM well, actually it is very easy for them to follow it up and implement it. And that's the reason I took it.
Okay.
So
So there is
this
one.
method,
Yes, I
yeah.
please continue. Please continue.
So yeah, so if you want to have an idea of all this method, we can refer to G.R. Lee's book. So I think mentioned somewhere. He has written a book on somewhere I mentioned.
Okay. We can get it if we follow that your lecture.
Yeah.
We can get that reference.
And this slide actually, this Meshfree method is moving beyond finite element method. So this particular book actually you can read. Actually, he has given a comprehensive review of all these techniques.
Okay. So there is one queries from that our professor. Here's the sir. I have a following queries. In a bar subject to tensile loading, what is the effect of assuming random e value on the failure behavior? Do the strain localized in region with higher e values?
What is that? Where is
In the
what is that?
so you can so you just click on that right side. There is one message box option is there. You just click it there. This two people symbol is there, and thereafter the symbol is there. Upside, yes, in the MS Team, in the MS Team.
Okay.
In the upside, you can see the two show participant option is there, and thereafter on. So what is saying? You just click and see the last comment.
So I have following query. In a bar subject to tensile loading, what is the effect of assuming random e-value on the failure behavior? Do the strain localize in region with the higher e-values? Yeah. See, the randomness in E doesn't make any changes in your this thing stress values, but your strains will be random. Now, what I assumed in some of the problems is damage. So damage actually you can have non-local damages that creates issues. Okay, you can have non-strain localization as you mentioned. Now, when you have E as random, okay, you have actually, if you look at different points, you have different your strain will also be random in nature. Okay, so you have strain randomness in nature, and this localization issues. Say 1T bar actually you don't have much issues like that. Okay, say for example, if I take a plate with the hole, then obviously you have near the hole you have strain localization even otherwise. Okay, so depending upon how the randomness is modeled, if you want to model a localized model, then actually you can model it as it is. Okay, I don't know whether that is a question. Did I answer your query?
Professor Mahendra, you can sir unmute yourself and you can talk to Professor also. Professor Mahendra. Okay.
Okay. So finally, this is.
He is commenting. Only he got the answer. His mic is not working, so okay. Please want to thank you.
So yeah, actually, I didn't expect it to be a failure analysis. I didn't extend that to a failure analysis. Okay, and probably for if I take a crack problem or something like that, I will extend that. Okay. And the moment I take the damage values, then actually that is something which I need to look at it.
We are not getting any queries from the other participant. Probably it is a tough topic for them because many have probably started finite element, just completed.
Like, either they understand everything or they didn't understand anything.
It is asking, sir, please suggest any book for MATLAB programming in for the AFM.
Oh, that is a tough question for me. You can have several books. Yeah, one book I'll reply. Probably I suggest this book to Askar Bhatti. Okay, book by Askar Bhatti. Okay, he's a professor in Iowa. He has written a good book, Introduction to, I think, FEM. And FEM, actually, you can see, you can even Professor Sheshu's book is also a good book. You won't get actually MATLAB code, inbuilt code in many of these books. You better learn the technique and start writing the code by your own. Actually, here what we used to do is when we teach FEM, we usually give programming exercises. Unless you program it, you won't learn it. Okay, if you want to learn it, you have to program it. Because it's a technique for programming, so you have to learn by programming by your own.
So what I understand yes, I continue.
Yeah, I don't remember any book specifically for MATLAB
FEM.
implementation. Yeah. So only Askar Bhatti, they have given some MATLAB or other numerical, some programming codes are available in that, I think.
Some book you may get some coding, but they are basically may concentrate on the truss and beam problem. But again, you will observe that in that case they are not using that. If they started from shape function, then you will get the concept. But if they directly use that matrix of element, and then that will not solve the purpose.
So you should construct the shape functions. You should use the Gauss feature, and you should assemble the element stiffness matrix, and like that you have to practice. Then it will help. It will be helpful for you to extend that for 2D and 3D. So 1D problem actually you can make use of stiffness method. Okay, that will give you. That will not give you an understanding in FEM.
For the reason I told that once you are able to do FEM coding for the cell element, because cell element anyhow you have to start from that shape function, all the things, 4-noded, 8-noded.
Shell will be difficult because
for the beginner it will be difficult. Yes.
Shell theory they need to understand.
Yes, that's also another topic. Yes.
Yeah, any 2D plane stress problem you can do. You start with the plane stress.
Basically, you have to start with the shape function and then you have to land up to the correct result. So once you complete it for a truss problem or a beam problem, you may have some confidence on the FEM. Then you can start that Meshfree method, and then you can compare the result. Okay, I hope that will give you the more confidence on the subject. Thereafter, you can proceed for stochastic and other Meshfree technique. Once you learn one Meshfree technique, you will find the rest of the things are almost similar, and you can do other type of method also. Okay, I don't have much question now. What I want to say that if for this type of research work, basically you do not need much research facility. Only the MATLAB and that few books.
You need to have a good computational facility, otherwise your simulations will lag.
No, so for the beginner, for the beginner, if they are handling with a big problem, that time their computational facility should be good. Yeah, that's true. But a small problem, and they can start. Because if you I want to go for that one bullet hitting a jacket and there's a large deformation problem, and you are using a large number of particles, all the things, that obviously the computational time will increase. And you will find that your laptop is taking 1 day to give one result. After that 1 day, you can come to know whether the result is correct or wrong. That also is one painful thing of the coding. And I think, sir, there is no available software, commercially available software in this Meshfree method, just like similar.
No.
Okay,
Carly
so
has developed, it's not commercially available.
okay.
For
Basically,
academic research,
yes, sir.
they have developed, but not, some academic research related softwares are available, but not. It's also not freely available. I think
Okay,
some teams, some specific research teams, they have developed something like, say, for example, Yarley's team, but now he has moved to a different area.
okay. So basically, they have to, those that want to do research in this topic, they have to start coding by themselves at that
Correct.
early stage from the BTech or MTech stage. They have to start coding. Otherwise, later on, you will not get so much time to do all the things. Okay. Thank you, Professor, for your that informative and very useful talk, because though it is tough, but we cannot ignore that things, because those who want to deal with some real life problem, and there is a lot of difficulties there in the finite element itself, because finite element sometimes cannot give correct result. In that case of large deformation and discontinuity, in that case anyhow you have to shift to Meshfree method. So, and we also should learn, and we also should encourage our BTech and master student to learn this type of technique, because this is the future. Because finite element almost is saturated. There is not much development in the finite element, and whatever development we are getting on the Meshfree method itself, you can see the SPH and other method, element free method. You see that all are developed in 2005, 2017, like that time. So basically, this is the I hope will be the future for our civil engineering application also. So I want to thank Professor Arun to spare his time to deliver a talk here. I hope some of our participants will be benefited from your talk, and later on probably they will also will go through this lecture again to understand that concept of Meshfree, and what sir is told that you have to go that some paper which is free level you can download, and you can copy the code, and you can run that small problem in your computer, and you can learn like that. Okay. So I want to thank Professor Arun to give some nice presentation.
Yeah, thank you for inviting me actually, and thank you all for listening to me patiently at this afternoon time. Listening to this kind of talk is very difficult.
Yes, that's true. Now, our participants, what I observe, they are very patient, and they are very much curious to know many things. What I observe, so probably they are lacking of some sort of resources, but they are eager to know many things, and they are regularly attending this kind of, and they are also asking us to organize such type of things regularly, so that they can also enhance their knowledge. So it may happen that in 2 hours they may not be able to directly jump to research, but they can come to know that what the research is going on in the international level, and what the IITs and other NITs or other top level institute are working on the topic. Okay, so they can come to know what the research is going on, and they can influence the student to work on that particular topic, because in that 4 or 5 days we are dealing different topics. So which one is suitable for them, they can choose and do research on that topic. Okay, so we are concluding the session here.